In order to present some applications of Gauss's law, we need to clarify the concept of Gaussian surface, as the key element of the law. We have defined electric flux by introducing an imaginary surface and determining the number of the electric field lines passing through that surface. When we proved Gauss's law, we applied a surface enclosing a source charge over which we evaluated the electric field due to the charge. We call such a surface as Gaussian surface. That is, Gaussian surface is any imaginary surface that encloses a charge or an arbitrary distribution of charge. Although Gauss's law applies to any closed surface, it is often convenient to choose such a surface which helps us to exploit the symmetry of the charge distribution. The electric field due to a symmetric distribution of charge also exhibits that symmetry in some form, and we can find a Gaussian surface on which the magnitude of the electric field is constant and the electric flux is normal or tangent to the surface. Let us consider some simple examples for Gaussian surface. The first one is a sphere S enclosing a point charge q in its center. If we forget about Coulomb's law, we can still suppose that there is no preferred direction around a point charge. Therefore the electric field E must be spherical symmetric around it, as the radial field lines demonstrate. Since the magnitude of the electric field is the same in every direction at a given distance from the source charge, it is constant over the sphere S. At the same time, the electric field is perpendicular to the Gaussian surface. Another example for Gaussian surfaces is a cylinder denoted by S around an infinite charged line with a constant linear charge density lambda. Since the electric field E for such a uniform distribution of charge has a cylindrical symmetry around the line, the electric field is normal to the curved surface of the cylinder and the magnitude of the field is constant over it. The electric field is tangent to the two parallel planes of the cylinder, that is, the field lines do not intersect them. The amount of charge q enclosed by the cylinder is the source of the electric field which we evaluate on the Gaussian surface. In the third example we also use a cylinder as a Gaussian surface denoted by S, which is cut I/2 by a uniformly charged infinite plane sheet perpendicular to the axis of the cylinder. Here the surface charge density sigma is constant over the plane. Since the electric field E points outward from the positively charged sheet and it is uniform, the field is perpendicular to the parallel bases of the cylinder and its magnitude is constant over them. The electric field lines are parallel with the curved surface of the cylinder and do not pass through it. The amount of charge q enclosed by the cylinder is the source of the electric field which we evaluate on the Gaussian surface. These examples demonstrate that we have two cases in the calculation of the electric flux through Gaussian surfaces. Where the electric field is normal to the Gaussian surface and its magnitude is constant, the electric flux through the surface can be evaluated by multiplying the magnitude E of the field and the area S of that portion of the surface. Where the electric field is tangent to the Gaussian surface, the field lines do not cross the surface, therefore the electric flux through that portion of the surface vanishes. With the proper choice of the shape of a Gaussian surface, we can decompose the total closed surface into partial surfaces over which the surface integrals of the electric field either reduce to a simple multiplication or vanish. The net electric flux over the total surface is just the algebraic sum of the fluxes through the partial surfaces. Now we start with the simplest example for the application of Gauss's law, where we determine the electric field due to a point charge. We have already seen that the electric field E due to a positive point charge q has a spherical symmetry around the charge, and points outward. By considering the symmetry of the electric field, we choose a sphere S with an arbitrary radius r as a Gaussian surface where the point charge is in the center of the sphere. As a result of such a choice, the magnitude of the electric field E is constant over the Gaussian surface and the field is perpendicular to the sphere. Gauss's law states that the surface integral of the electric field E over the sphere S is equal to the charge q enclosed by the sphere over epsilon naught. For the sphere S, the surface integral is given by the magnitude of the electric field E over the sphere, times the surface area S of the sphere, which is equal to 4 pi times the square of the radius r of the sphere. Then q over epsilon naught is equal to 4 pi times r squared times E. If we express the magnitude E from this equation, we can see that the magnitude of the electric field is equal to 1 over 4 pi epsilon naught, times q over r squared. Since we know that the field is spherically symmetric, we can conclude that the electric field E due to a point charge q at the distance r from the point charge is given by 1 over 4 pi times epsilon naught, times q over r squared, times the vector r by the distance r. Here the vector r points from the source charge q to an arbitrary point at the distance r. We already derived this formula for a point charge from Coulomb's law. We will obtain Coulomb's law from this formula, if we place a point charge q' at the distance r from the source charge q and determine the electrostatic force F acting on the charge q' in the electric field E. The magnitude of the force is given by q' times the magnitude of the electric field E at the distance r from the source charge q. If we substitute the result obtained from Gauss's law into this equation, the magnitude of the force can be written as 1 over 4 pi times epsilon naught, times q' times q over r squared. Since the electric field is spherically symmetric around the source charge q, that is the force exerted on the charge q' points radially outward from the charge q, we can state the following. The force F is equal to 1 over 4 pi times epsilon naught, times q' times q over r squared, times the vector r divided by its length, which is Coulomb's law. In the next example we apply Gauss's law to determine the electric field for a thin spherical shell of uniform surface charge. Here we can see a spherical shell S with the radius R, which has a uniform distribution of charge with the total amount of charge Q. Due to the homogeneous distribution of charge over the shell, the electric field E is spherically symmetric, and the field lines point radially outward from the positively charged shell. If we examine the electric field outside the shell, we can choose a sphere S1 with a radius r greater than R as a Gaussian surface, which encloses the charged shell. For such a choice, the magnitude of the electric field is constant over the surface S1, and the field lines are perpendicular to the sphere. Here the integral of the electric field E due to the charged shell over the sphere S1 can be written as the magnitude E of the field over the Gaussian surface, times the surface area S1 of the sphere, where the area is equal to 4 pi times r squared. Since Gauss's law states that the surface integral is equal to the charge q enclosed by the sphere over epsilon naught, we can express the magnitude E from this equation. Then the magnitude E of the electric field outside the shell is equal to 1 over 4 pi times epsilon naught, times q over r squared. In order to study the electric field inside the shell, we choose a sphere S2 with the radius r smaller than R as a Gaussian surface. The surface integral of the electric field E over the sphere S2 is equal to the magnitude E of the field over the sphere, times the surface area S2 of the sphere, where the area is given by 4 pi times r squared. Gauss's law states that the surface integral over the sphere S2 is equal to the charge enclosed by the sphere over epsilon naught, but there is no charge inside the sphere. As a result, the surface integral vanishes and so does the electric field over the Gaussian surface. Since the radius of the sphere is less than the radius in the shell but otherwise arbitrary, the electric field must be zero inside the shell. Then we conclude that the electric field E due to a uniformly charged spherical shell with the total positive charge Q is the following. In an arbitrary point outside the shell, it is given by 1 over 4 pi epsilon naught, times the charge q over the square of the distance r between the center of the shell and that point, times the vector r pointing from the center to that point divided by its length. Whereas the electric field vanishes inside the spherical shell. This formula also shows that the uniformly charged shell with the total charge q is equivalent to a point charge q placed in its center. In other words, the electric field outside the shell is the same as if the entire charge were concentrated at the center of the shell. Here we plot the magnitude of the electric field E as a function of the distance r from the center of the spherical shell S. The graph shows that there is no electric field inside the shell, that is the magnitude of the field vanishes at distances from the center less than the radius R of the shell. Outside the shell, that is at distances greater than the radius R, the magnitude of the electric field follows the inverse square law, and it reaches its maximum value at the surface of the shell, which is equal to 1 over 4 pi epsilon naught, times q over the square of R. In the following example of the application of Gauss's law, we determine the electric field due to a uniformly distributed charge in a sphere. Here we can see a uniformly charged sphere S of the radius R with the total charge Q. Due to the homogeneous distribution of the positive charge within the sphere, the electric field E is spherically symmetric both inside and outside the sphere, and the field lines point radially outward from its surface. For the sake of simplicity, we omitted the field lines inside the sphere. If we examine the electric field outside the sphere S, we can choose a sphere S1 with a radius r greater than R as a Gaussian surface, which encloses the charged sphere. For such a choice, the magnitude of the electric field is constant over the surface S1, and the field lines are perpendicular to the surface. Here the integral of the electric field E due to the charged sphere over the Gaussian surface S1 can be written as the magnitude E of the field over the surface, times the area S1 of the surface. This area is equal to 4 pi times r squared. Since Gauss's law states that the surface integral is equal to the charge q enclosed by the Gaussian surface over epsilon naught, we can express the magnitude E from this equation. Then the magnitude E of the electric field outside the sphere S is equal to 1 over 4 pi times epsilon naught, times q over r squared. In order to study the electric field inside the charged sphere S, we choose a sphere S2 with the radius r smaller than capital R as a Gaussian surface. The surface integral of the electric field E over the sphere S2 is equal to the magnitude E of the field over the Gaussian surface, times the area S2 of the surface, where the area is given by 4 pi times r squared. Gauss's law states that the surface integral over the sphere S2 is equal to the charge q prime enclosed by the sphere S2 over epsilon naught. Since the charge is uniformly distributed throughout the sphere S, the amount of charge enclosed by the sphere S2 is proportional to its volume. As a result, the charge enclosed by the sphere S2 bears the same proportion to the charge enclosed by the sphere S as the volume of the sphere S2 to the volume of the sphere S. The volume of a sphere is proportional to the cube of its radius, and we can write that the charge q prime enclosed by the sphere S2 is equal to the cube of the ratio of its radius r to the radius capital R of the sphere S, times the total charge q distributed within the sphere S. If we substitute this expression into the surface integral and express the magnitude E from the result, we obtain 1 over 4 pi times epsilon naught, times q over the cube of capital R, times r. Then we conclude that the electric field E for a uniformly charged spherical sphere of the radius capital R with a total positive charge q is the following. In an arbitrary point outside the sphere, it is given by 1 over 4 pi epsilon naught, times the charge q over the square of the distance r between the center of the sphere and that point, times the vector r pointing from the center to that point divided by its length. In an arbitrary point inside the sphere, the electric field E is equal to 1 over 4 pi times epsilon naught, times q over the cube of capital R, times the vector r. This formula also shows that the uniformly charged sphere with the total charge q is equivalent to a point charge q placed in its center. In other words, the electric field outside the sphere is the same as if the entire charge were concentrated at the center of the sphere. Here we plot the magnitude of the electric field E as a function of the distance r from the center of the sphere S. The graph shows that the magnitude of the electric field is directly proportional to the distance from the center inside the sphere, that is at distances from the center less than the radius capital R of the sphere. Outside the sphere, that is at distances greater than the radius capital R, the magnitude of the electric field follows the inverse square law and it reaches its maximum value at the surface of the sphere, which is equal to 1 over 4 pi epsilon naught, times q over the square of capital R. After having studied spherically symmetric electric fields, let us see how we can apply Gauss's law to determine the electric field for a uniformly charged infinite line, where the linear charge density lambda is constant along the line. We have already seen that the electric field for such a distribution of charge is cylindrical symmetric along the line. If the charge density lambda is positive, then the electric field E points radially outward from the line of charge. Therefore, we can choose a cylinder S with arbitrary radius r and the height or length L as a Gaussian surface such that its axis is along the charged line. For such a choice, the electric field lines are perpendicular to the curved surface of the cylinder and the magnitude of the electric field is constant over the surface. At the same time, the field lines are parallel with the two bases of the cylinder and do not intersect them. The electric flux through the cylinder is given by the surface integral of the electric field over the cylinder, which can be split into the integrals over the three parts of the cylinder, the curved surface and the two bases. Since the field lines do not intersect the bases, the flux through them vanishes. Then the integral of the electric field E over the Gaussian surface S reduces to the integral over its curved surface, which is equal to the magnitude E over the surface, times the area S of the surface. The area of the curved surface is given by the product of the circumference of the bases, times the height of the cylinder, that is 2 pi times r times L. As a result, the electric flux through the cylinder is equal to 2 pi times r times L times E. Gauss's law states that the electric flux through the Gaussian surface S is given by the charge q enclosed by the surface over epsilon naught. Here the charge q is equal to the linear charge density lambda times the length L. If we express the magnitude of the electric field E from this equation, we can write it as lambda over 2 pi times r times epsilon naught. Since the radius r of the Gaussian surface is arbitrary, we conclude that the electric field E at the distance r from a uniformly charged infinite line with the charge density lambda is given by 1 over 2 pi times epsilon naught, times lambda over r, times the vector r divided by its length. Here the vector r is perpendicular to the charged line and points from the line to any given point at the distance r from the line. This result also provides a good approximation for the electric field due to a uniformly charged thin wire with a finite length in the vicinity of the wire far from its ends. Here we plot the magnitude of the electric field E around the line as a function of a distance r from the line, and the graph demonstrates that the electric field strength is inversely proportional to the distance r. By applying Coulomb's law we already obtained this formula for the magnitude of the electric field. However, we can see that it is easier to derive the same result if we use Gauss's law. In the next example we apply Gauss's law to determine the electric field for a uniformly charged infinite plane, which we have already done by using Coulomb's law. When we considered such a plane with a constant surface charge density sigma, we saw that the electric field E has a reflection symmetry across the plane. The field is perpendicular to the plane and points outward from it. If the plane is positively charged, that is, sigma is positive. We can exploit this symmetry of the field if we choose a cylinder S with an arbitrary size as a Gaussian surface, which is cut in half by the plane and its bases are parallel with it. Then the electric field due to the uniform surface charge over the plane is perpendicular to the bases of the cylinder, and its magnitude is constant over them. At the same time, the electric field lines are parallel with the curved surface of the cylinder and do not pass through it. If we calculate the electric flux through the Gaussian surface S, we can split the integral of the electric field over the cylinder into the integrals over the curved surface and the bases of the cylinder, where only the surface integrals over the bases give contributions to the flux. Then the electric flux is equal to 2 times the magnitude of the electric field over the bases times the surface area S of the bases. Gauss's law states that the surface integral of the electric field E over the cylinder is equal to the charge Q enclosed by the cylinder over epsilon naught. The total charge Q enclosed by the cylinder is given by the surface charge density sigma, times the area S of the intersection of the plane and the cylinder. We can express east from this equation and see that the magnitude of the electric field around the uniformly charged infinite plane is given by its surface charge density sigma divided by 2 times epsilon naught. We have just demonstrated again that the electric field of such a charged plane is constant and does not depend on the distance from the plane. We also obtained this result by applying Coulomb's law, but this method using Gaussian surfaces adapted to the symmetry of the field is far more simple. Based on this result, we have already determined the electric field produced by 2 infinite parallel planes, which have opposite charges with the constant surface charge densities plus and minus sigma. The electric field E sub plus due to the positively charged plane is uniform with the magnitude of sigma over 2 times epsilon naught. The uniform electric field is perpendicular to the plane and points outward from it. The electric field E sub minus due to the negatively charged plane is also uniform and has the same magnitude, but points inward. When we applied the principle of superposition of electric fields, then we saw that the electric fields E sub plus and E sub minus cancel each other out outside the space between the planes, and the net electric field E is 0. We also saw that the 2 electric fields in the space between the planes point in the same direction, therefore their superposition gives the uniform electric field E with the magnitude of sigma over epsilon naught. The field between the plates points from the positively charged plane to the negatively charged one. This example demonstrates that the combination of Gauss's law and the principle of superposition of electric fields provides an efficient method to determine the electric field due to even more complicated distributions of charge, if the geometry of the field exhibits some symmetry.